Welcome to week 4, the problem of the week, rolling races. It's entitled Rolling Without Slipping, the Race to the Bottom. In this problem of the week, we're going to do a quantitative analysis of the rolling down the ramp races that we did during the laboratory, and we're going to start with an energy analysis. And one thing to point out is I haven't actually explicitly told you whether it's the sphere or the hoop or the disk. It turns out all of that information is summarized simply in the moment of inertia. So let's get our notation together. The mass of the object is going to be m. The moment of inertia is going to be I equals c mr squared, where c is a constant, and the radius of the object that's rolling is going to be r. At the start, the potential energy is given by mgh, where h is the height of the ramp. By the time it rolls to the bottom of the ramp, all of that potential energy has been converted into kinetic energy, but we have to keep in mind the kinetic energy is composed of both the motion of the center of mass, that translational motion of the center of mass, and the rotational motion about the center of mass. So we can equate the energy, and we find that mgh is equal to 1/2 mv squared, that's the motion of the center of mass, plus 1/2 I theta dot squared, where theta dot is the angular rotational velocity of the object when it's at the bottom of the ramp, and I is the moment of inertia, as we discussed previously. Okay, these objects roll without slipping, so there's a constraint between how fast it can rotate and how fast the center of mass is moving, and that constraint is that the velocity is equal to r times theta dot. If we substitute that into the energy relation, and we find by substituting in I equals c mr squared, we're going to have an m in every term that we can cancel, and we then go ahead and solve for v. What we find is v will equal 2gh over 1 plus c. Now notice this final velocity at the bottom of the ramp is independent of the mass of the object. So it doesn't matter what the mass is, it's independent of the radius of the object. All that matters is the constant c. So whichever object has the smallest c will have the largest velocity at the bottom. Well, if it has a larger velocity at the bottom, that meant it had a larger velocity all the way through, which means it got to the bottom of the ramp faster. So this analysis tells us that objects that have smaller moments of inertia will have larger velocities. In particular, if I look at something that just slides down the ramp, if there's no friction, and has no rotational motion whatsoever, I can replace the c by 0, and that will be the object that would win in any of the races because none of the energy goes into causing the object to rotate. One other point I want to make out is if we were comparing objects with different heights, we have actually done an approximation here. The height that should go into that energy formula should be the height of the center of mass. We took that to be the height of the incline, but it's really the height of the incline plus whatever the height of that center of mass is above the incline. That height can be slightly higher than h, which means there could be a small dependence on r in the numerator, but typically that small dependence on r in the numerator is tiny compared to the dependence on c that appears in the denominator for the velocity. So this analysis that we're giving is slightly simplistic, but it is not so bad, and as we saw with the races themselves, it worked very well. Okay, let's do a little bit more of an analysis. I just want to recap here that the smaller c gives the larger v, which is going to win the race. So now we're going to go on to a more in-depth analysis looking at equations of motion rather than just energy, and we're going to look directly at the dynamics of the system. So in order to do this, we have to look at the forces, and in particular, we have to separate the forces into the forces along the ramp direction and the forces perpendicular to the ramp direction. Of course, the forces perpendicular to the ramp direction must cancel because there's no motion perpendicular to the ramp. And then the motion or the forces along the ramp direction are going to tell us exactly what's going on with the motion. and it's effectively reducing this problem into a one-dimensional problem. So what are the forces that we have? Well, obviously we have the effect of gravity, which is going to be downward and acting at the center of mass. We have a normal force at the ramp, which is keeping the object from falling through the ramp, and that is going to be perpendicular to the surface of the ramp. And then we have a frictional force that is parallel to the direction of the ramp that ensures this constraint of rolling without slipping. And so now if we look at those forces, what we see is that the force down the ramp due to gravity and the normal force is indicated by that purple arrow. That has a particular magnitude. But then there's a force that's opposing it due to friction, which must be smaller than that. And it's the net force, the difference between the force due to gravity oriented along the ramp direction and the force of friction that's going to give us the net force or the acceleration. So then applying Newton's laws, we'll get the mass times the acceleration is equal to mg sine alpha minus the force due to the friction. Okay, that's not enough for us to solve because we don't yet know what the force due to friction is. So we now have to look at the torque acting on this object. And similar to the Newton's law for linear motion, Newton's law for angular motion is going to be the moment of inertia times the angular acceleration is equal to the torque applied. Well, the moment of inertia is just cmr squared, and the torque is just the radius multiplied by the force of friction, because that force of friction is perpendicular to the object at the point where the force is being applied. Now, if you look at this, we can cancel an r from both sides of the equation, and we furthermore can use the rolling without slipping constraint, which says r theta double dot must equal the acceleration, and then we get this equation cma is equal to f friction. So I'm going to take that, I'm going to substitute in for F friction in our first equation. I'll get a C minus CMA. I'll bring that to the left-hand side. The M's are going to cancel, and I'm going to solve for the acceleration. And when I do that, I get the acceleration is g sine alpha over 1 plus c. All right, great. We found the acceleration. Now we know that the initial velocity and initial angle are 0, and we know our initial rotational frequency is 0. We know the initial position and the initial angle are 0. So we can immediately determine how long it takes for the object to go down the ramp by using this acceleration. So the distance that an object travels that is in uniform acceleration over a particular time is just 1/2 at squared. The total distance we need to go is the height divided by sine alpha. That's the hypotenuse, or the length along the ramp. And solving for the total time, we get the square root of 2h 1 plus c over g times sine squared alpha. Now, once again, no m dependence, no r dependence to this. The only thing that matters is the c, and whichever object has a bigger c is going to have a longer time. So once again, it tells us that the objects with the bigger c are going to lose the race. Objects with the smaller c are going to win the race. Now we can do one final check. We can take the acceleration, multiply it by that time. That'll tell us what the velocity is at the end at the bottom of the ramp. And when we work that out, what we find is that the speed at the bottom of the ramp is the square root of 2gh over 1 plus c. And that's exactly the same as the answer that we had before. So all of these results agree with one another. Once again, if I really wanted to be very specific, I could do the slight modification to take into account how h does have some r dependence to it. But as we discussed before, that r dependence is relatively weak, and we don't expect it to have a significant effect on the results.